All right, everybody, so today we are starting Chapter 2, Lesson 1, and we're going to start talking about some proofs, maybe some things that you'll need to refresh on, but we will be diving into that for this next chapter. So let's get started with some inductive reasoning. Now, inductive reasoning we define as making a conclusion based on observations and patterns. So that would be like saying that, oh, the sky is gray, right? So that means that the sun is not shining. Or normally, if the sky is dark, that means that a storm is coming. So some of those different things that we can recognize patterns of, or our observations that we can say come to a conclusion with. A conjecture is a concluding statement reached using inductive reasoning. So that would be our final conclusion that we come to. Conjecture is just another word for saying conclusion. It's just a more proper way for saying that we have used those observations and patterns in order to be able to come to this conclusion. So let's take a look at a couple of examples. We can do this with numbers. So like example 1 here, we would have 38 to 31, 31 to 24, 24 to 17. Well, you might notice that these are decreasing by 7 each time. So we can continue that pattern with 10, 3, negative 4, negative 11, and negative 18. The conjecture here, or our concluding statement, would be subtract 7 from previous term to get next term. So 17 was our previous term. To get its next term, we minus 7 to get 10. Couple more examples here, but I want to jump down to some that might be a little bit more confusing. Specifically, let's look at number 4. We go A, D, G, J. Well, you might notice these are letters of the alphabet, and they're in a specific order where we skip 2. So B, C would be in between, E, F, H, I, J, then we'd have K, L, M, N, O, P, Q, R, S, T, U, V, W, X, and Y. So to say this conjecture, we would skip 2 letters after the previous term. So we skipped 2 letters every time. Our conjecture could simply be to skip 2 letters after the previous term. But what about this next one? 7, 30, 7, 55, 8, 20. Well, these are all times on a clock. And to go from 7:30 to 7:55 is gaining 25 minutes later. So 25 minutes later there. We'd also go 25 minutes later to get to 8:20. 25 minutes later from 8:20 would be 8:45. So 25 minutes is our pattern. And we're just going to keep adding 25 minutes to our time to get 9:10, 9:35, 10 o'clock, 10:25. So our conjecture here would be add 25 minutes to the previous time. Sometimes, though, they can be crazy number patterns, like number 6. Number 6 is a little bit of an interesting number pattern. We have 3, 1, 4, 1, 5. Well, we're not adding, subtracting, multiplying, dividing, nothing like that to get those next terms. What this really is are all the digits of pi. So you might have to look some of these up. 3.14159, 2, 6, 5, 3. Those would be the next few digits of pi. And our conjecture would say that each digit is the next digit in pi. So sometimes our conjectures are patterns of adding or subtracting. Sometimes they're skipping certain steps. Sometimes we can think of it as time, maybe shapes, and we're adding on a new side to a shape. Other times it might be a digit. We're adding on the next digit of pi or some other large number. If you want to try those other couple of examples, I will have that posted here in a second so you can see this full page to see the full answers of everything. So this would be a good time to pause and do those two examples. All right, and so here would be that key for those problems 2 and 3. So if you want to pause and catch up with those. So continuing on with our different things that we'll be talking about, we also have things called counterexamples. A counterexample is an example that shows a conjecture false. So when you think of what a normal example would be, it shows how something works. We do examples in class all the time. A counterexample, that word counter in front of it, says that it's going to do the opposite. It's a counterexample. So instead of showing how something works, it shows how something is false. And we're specifically going to use those for a few of our conjectures that we have here. Let's just do problems 1 and 2 for right now. So for the first example, we have the sum of any 2 consecutive integers is always odd. Well, we can test that out. Let's say we take 0 plus 1. Because integers, we can take 0 and 1, and we would say that that gives us 1. 1 is odd, so we're good there. What about 1 and 2? Well, 1 and 2 would give us 3. That's also odd, so we're good there too. What if I take -1 plus -2? Well, that would give us -3. So we have to think back on what our integers are. Those are all the positive and negative whole numbers. When we say consecutive, that means that it comes next in order. So consecutive 0, 1, 2, 3, we want to make sure that we're adding them in the right way. This works because of how our consecutive integers work. Anytime you have an odd number plus an even number, like we do here, here, and here, or any other of these examples, we will always get an even number. The only way to get an even number when you add 2 numbers together is if they're both even. When you add 2 odd numbers together, that's also going to be an even number. So the only way to get an odd numbered outcome is to take an even and an odd number, which is exactly what happens when we take 2 consecutive integers. This is true. So some of these, you might have to do a little trial and error. We kind of show that here by trying out some of what consecutive integers means. The next one, though, we have the product of 2 numbers is always larger than either number. Unlike the first example, this just says any 2 numbers. So it doesn't matter if we're using fractions, decimals, whole numbers, doesn't matter. Let's try one. Let's say that we take 3 times 2. Well, we know 3 times 2 would give us 6. So that wouldn't be smaller than 3 and 2. So that doesn't disprove this at all. What happens though when we take a fraction times a fraction? What if I take 1/2 times 1/3? Well, remember how we multiply fractions. We take the tops multiplied together, 1 times 1, over the bottoms multiplied together, 2 times 3. So 1/6. The product of two numbers is always larger than either number. Well, in this case, that's false. 1/6 is half of a third. So that means that it's smaller than both a half and a third. So we can use this example here to say that this is false. You could do this with any two fractions. You could also do this with any whole number and a fraction, and you'll get the same result. So I'm going to let you go ahead and try the next few examples. I will post the key here in just a second. So this would be a great time to pause the video to give these a try. All right, and here is that key of those counterexamples. So if you want to pause, double check, make sure that you have those right. The last part of this is for you to try and write your own conjecture. I'll be talking about your own conjectures the next time that we do notes, which will be Friday. So if you want to try a couple of examples so I can check those out on Friday, that's what we will start off with class. There's a Delta Math, or not a Delta Math assignment, there is a worksheet for you to do in Schoology. So you can do that on a separate piece of paper and upload that to the assignment Dropbox for the day. Other than that, this was all that we had for today. Make sure that you study for your test, and I will see you next time.